Diffusions. We've seen one or two definitions of them now. We've seen one or two sort of examples of what we think they ought to look like. We haven't yet seen a definite example of one other than trivial ones with speed 0. So that's what we're going to try and do in this section. We're going to cover construction of diffusions. So just to remind you, here's a definition of an diffusion. It's a stochastic process, xt, in continuous time t, such that each increment of the process over a time delta t has at least approximately a normal distribution. That is, it's an approximation that should be good if delta t is small, conditional on having known already everything that happened up to time t. The ut here is called the drift, and the vt the speed. So those are things that determine the local mean and variance of those increments. You might have noticed that that's a descriptive definition. It says what a diffusion ought to do. This is what we would like it to do. We would like to have a stochastic process that behaves like this. But how do we actually get one? Now, it's more difficult to do this in continuous time than it is in discrete time. In discrete time, with the random walk, the question of construction is not quite so mysterious. All you have to do is, if you want to, say, do a simple random walk, a construction. How do we do it? Well, we just say let there be some random variables, y1, y2, infinite sequence, be independent, identically distributed, plus or minus 1 with probability 1/2 each, and let xn be the sum of the first n steps. And there we are done. We've defined some random variables that give where the walk has got up to, xn, at time n, that is after n steps. So that's all pretty straightforward, but of course that only works because the points in time at which we have to define where the walk has got up to are just the integers. So we can just go 1, 2, 3 and run off a random variable for each step that gets us there. To do that in continuous time, so never mind that, we're going to continuous time now. Well, we can't really have a step in continuous time because as soon as we take a step it'll be too big. As soon as we take a time step of any length, we have to think about all the stuff that we skipped over when we took that step. So in that context it's useful to know this little fact. Say we have a random variable that is normally distributed with mean 0 and variance sigma squared. Then we can split that random variable up as the sum of a z1 and a z2, where the z1 and the z2 are independent, identically distributed, normally distributed, mean 0, and half the variance. You're probably familiar with the fact that if you started with the z1 and z2, knowing they were independent and knowing that they each had mean 0 and variance sigma squared over 2, then if you add them together, you'll get something which is normally distributed with mean 0 and variance sigma squared. We use that quite often. Here we're going the other way. We're starting with the z and splitting it up into a z1 plus z2. And this is really easy to do as long as you accept that we can always make up new random variables that are independent of any random variables that we've thought of so far. In this case, all we have to do is make up one new random variable, call it z prime. It's going to be normal 0 sigma squared and independent of z. So now we've got two random variables, z and z prime, independent and both with this distribution. And now we just do this. Z1 can be the average of z and z prime, and z2 can be a half of z minus z prime. And if you just look at those, you can check that, yep, z1 and z2, if you add them together, you get z. Z1 and Z2 are both normally distributed with mean 0 and variance sigma squared over 2. That's easy to check. And in fact, the covariance, if you care to work it out, of Z1 and Z2 is 0, which means that Z1 and Z2 are independent. So, done. That's how you do it. You can split up any normal random variable Z as the sum of two smaller random variables by this trick. And all you have to do to make that happen is to be able to introduce one new random variable that was independent of Z. Okay, let's have a go at doing the construction of the Ito diffusion on the time interval 0 to t. The definition of Ito diffusion doesn't say anything about what the initial value is supposed to be. It only talks about differences, so let's just make the initial value be 0, like that. Now then, what we're going to do as a first approximation, we're going to treat the whole time interval from 0 to t as if it were a single time step. So that's just one time step, which means that the distribution of the change in the process, the increment of the process over that one time step, should have approximately a normal distribution. So as a first approximation, let's make it have a normal distribution. Let's first step, let there be a random variable z0 which has a normal distribution, mean 0 and variance t. Notice I'm using the superscript 0 just to as part of the name of the random variable here. That's all that signifies. And I've made it to have variance t because that will correspond to what the variance of the step is going to be. And then my process will be defined like this. Its value at time t will be given like that. That corresponds to what the increment was supposed to be over a time interval. Here delta t, the mean of the increment is supposed to be proportional to delta t, and the variance is supposed to be proportional to delta t as well. So here I've made my mean proportional to delta t, the constant being the value of u, and the variance proportional to delta t as well. I've got that to happen by putting the t in there. So delta t is all of capital T in this one-step approach. So then what that looks like is we've got some value given like that at time capital T, and in between I'll just fill it in as a straight line. Okay, done. That's our first approximation. That's a random function defined on the interval 0 to t, and in some sense it's a very rough approximation of what the Ito diffusion is supposed to do. Notice, by the way, I've written u0 and v0 here. Those are just the values that the u and the v have at time 0, And those are assumed to be known at time 0 because u and v were measurable with respect to the filtration. So they're known, and then once we go beyond time 0, we just have a straight line up to the value we chose for time t. Okay, second step, maybe you can guess what's going to happen now. That one normally distributed random variable, we have to split it in half so that we can now do things in 2 steps of half the length. So we're now going to have Z1, 1 and Z1, 2. And these are going to be IID, like so, with like that. So whereas before we had one normally distributed random variable associated with the whole time interval, now we've got 2 independent normally distributed random variables associated with the 2 subintervals of length t over 2. And now we're going to have something we'll call x1, another random function. It'll again be 0 to start with. At the time point t over 2, it will be like that. So similar construction to before, but now we've only got t over 2 of time. And at time t, it'll be what it was at t over 2 plus like that. So now we've defined some values at times t over 2 and at t. So something like this. And in between we'll fill in straight lines again like this. Notice that the value at time capital T is not quite the same as it was for the first approximation. So this is x0 and this is x1. They're not quite the same at time capital T, although if u and v were constants, it would be the same. If you look at the way this thing is written to add up, we've added up u0 times t over 2 plus u t over 2 times t over 2. So if both of those u values were the same, we would have the same as what we've got here. And similarly with the v's, if these two v values should happen to be the same, then we've got the sum of these two normally distributed random variables, which gives us back z0 again. So approximately it's the same value at these 2 points, except that the u and the v might have changed between time 0 and time t over 2. Next step, now we're dividing the time interval into 4 parts of length t over 4, and so this time we're going to split up our normally distributed random variables like so. We're going to have z2 1 and z2 2, which will add up to what our first one was before, and z2 3 and z2 4, which will add up to what the second one was at the previous stage. And we'll define our process x2 like this. At time 0 it's still 0. At time t over 4 it will be that plus that. At time t over 2 it'll be what it was at time t over 4 plus and now we need the next of our random variables. One time step later, it'll be t over 2. And finally, fourth little step takes us to time t. Right, so that defines values for our random function at time 0, t over 4, maybe there, t over 2, maybe there, 3t over 4, and at time t. And in between we linearly interpolate, so now we've got a random function that looks like this. And it will sort of approximately agree with the previous one at the time points where they're both defined, at t over 2 and at t. Not exactly, because u and v have changed along the way, so we're not getting exactly the same values, but if u and v have not changed too much, then it'll be kind of close. After a couple of more stages of this, we can now see what it would look like by the time we've split up the time interval into 16 parts. So now we've got 16 little linear pieces, and you see we're starting to get a jagged kind of function that's beginning to look a bit like the ones in the pictures that I handed out. This is what an Iterative characteristically looks like. It looks like it's proceeding by a lot of very small steps. If you like, it's a sort of a continuous time random walk, but the amount of variability in it can vary quite substantially because that's controlled by the u and the v, and the u and the v can themselves be random processes. So on different realizations, different outcomes in the sample space, you can end up with these random functions that look quite different, as in the pictures seen here. Same process, just different outcome. All right, well, we're not quite there yet because all we've got so far is a whole lot of random piecewise linear functions, so none of them is quite an Iterative. What we've got to do for a final step is get our final process x of t, the one we were really aiming for, to be the limit as that process we just went through of halving the length of the time interval and then halving it again and so on repeatedly. Whatever function that converges to, that's the one we want. That's our Iterative. Now the convergence is not a simple topic. The convergence of sequences of random variables is really a subject in itself that we don't have time to go through systematically. So I'm just going to note down now the particular senses in which this convergence can be said to occur. And there's about 3 that I have to make a note of. One is what's called convergence in probability. And this just says for any small quantity epsilon greater than 0, the probability of making a large error, which is to say this is the sup, that is the maximum or supremum, so the maximum difference between the approximation and the supposed limiting process, the probability that that's anywhere greater than epsilon should converge to 0. That's convergence in probability. Secondly, there's convergence in quadratic mean. Which again involves this supremum. Again, we want this to be small, so in quadratic mean we just say the expected square of it should be something that converges to 0. So that's a random variable converging to 0 in that sense. Then there's convergence with probability 1, which is what you probably thought it was in the first place. So this is again looking at the same error. That should converge to 0, but if we just leave it as a random variable converging to 0, then it may converge to 0 or it may not, depending which outcome in the sample space you get. It's a random variable after all, or a sequence of random variables here, so that it converges to 0 is an event, and we could consider the probability of that event, and what we want is for the probability of the event to be 1. That's convergence with probability 1. I'm not going to make too much of a big deal of all these different types of convergence in this course, just to say that in the particular case we're looking at here, the construction of an Ito diffusion, all three types of convergence hold. So the convergence of the sequence of successive approximations to the actual Ito diffusion, it converges in all three of these senses. The one that we'll probably make the most use of actually is the second one, the convergence in the quadratic mean, if we ever have a need for that. Alright, so that's the explicit construction of Ito diffusions done. I think it was worth going through that because we will actually come back to this when we come to consider what the properties of Ito diffusions are in the next few lectures. So from a construction like that, this is where we end up with stuff like this in these pictures, these random functions. That's all they are, they're random functions, but constructed in this particular way.